Today we're going to talk a little bit about energy, and we haven't really talked about energy so far this semester. The only time we've really mentioned it is temperature changes and chemical reactions and energy transfer. So we're going to go back and review a little bit from chapter 3, which we skipped early on in the semester, which introduces energy, and then talk about how we can calculate how much energy is transferred in a chemical reaction. So what is energy? Energy is defined as the ability to do work. And work, conversely, is any activity that requires energy. And these are terms that you've heard in everyday life, so they shouldn't be so foreign to you. And there's two different kinds of energy that we're going to talk about. One is kinetic energy, and kinetic energy is the energy of motion. So, for example, as this bike rider is going up the hill, he is putting in energy because he is moving up the hill. All right. Once he reaches the top, he can just sit there for a moment, and at that point he has potential energy. Potential energy is determined by the position of an object or by the chemical composition of an object. And potential energy is basically stored energy, all right? So an object that's not in motion but could potentially do work has potential energy, and an object that is in motion has kinetic energy, whether it's energy coming, being used to go up the hill or energy from coming down the hill. It doesn't matter whether this process is spontaneous or non-spontaneous. Kinetic energy is just the energy of motion. Okay, so in a chemical reaction, we talk about this in terms of the movement of heat, okay, because that's usually how we can sense a change in energy. So an endothermic reaction is one where the products have more energy than the reactants. And in order for that to be true, what has to happen is that the chemicals have to actually pull energy from their environment while the reaction is happening, and the result is that the reaction feels colder. So the products are holding more energy, but they had to get that energy from their environment, and so that you feel that as the removal of heat. Okay, an exothermic reaction is one where the reactants have more energy than the products, and so as the reaction happens, heat is released or energy is released, and so these reactions actually warm up as they progress. And I use the term heat pretty freely here, but it's just because it's a term you probably are familiar with. But heat on a molecular level is associated with the motion of particles. And so heat comes from, or heat is a measure of thermal energy, and so every substance has some amount of heat associated with it unless it's at absolute zero. So every molecule or atom, even those in a solid, have some amount of motion unless they are at absolute zero. And the unit we use for heat is the joule, which is a capital J. So now in terms of reactions, how do we use these values? So we have something called the heat of reaction, which is just the difference between the energy of the products, or the heat in the products, and the heat in the reactants. And we call it delta H often, and it just tells you the amount of heat that's either absorbed or released during a chemical reaction. Okay, and so for an exothermic reaction, that value is going to be negative. We'd get a negative delta H. And for an endothermic reaction, we would get a positive delta H. All right, so let's do an example now. So we have water breaking down into hydrogen gas and oxygen gas. And it says here that our delta H for this reaction is positive 572 kilojoules. And so what that means is that for every mole of this reaction, 572 kilojoules of heat is absorbed. All right, absorbed means that the reaction is going to require energy in order to happen. And so that should make sense to you in terms of what you know about water. It doesn't just randomly break apart into hydrogen and oxygen gas. We have to put in energy, usually in the form of electrolysis, to get that reaction to occur, because hydrogen and oxygen gas have a lot more energy than the liquid water does. All right, so for this reaction, it says, suppose that we have 9 grams of water that reacts according to the equation above. How much heat is absorbed? Okay, so the thing about adding these energies into our problems is that it's just like the problems we've already done with our mole-mole fractions, except now instead of a mole fraction, we're going to have a mole on one part of our equation and the energy on the other. So let's do the example. So what we need to do is go from grams of water to moles of water because our chemical equation doesn't tell us anything about grams. So we always need to go to moles. And then once we have moles of water, then we need to use our delta H and our coefficients to get to the energy. Okay, so we're going to do 9 grams of H2O in the front. That's what we're given. And that's going to be times 1 mole of H2O is 18.02 grams. Okay, and then there are 572 kilojoules released, or absorbed, 572 kilojoules absorbed every time 2 moles of water reacts. And that's because we have a 2 next to H2O in our balanced equation. Okay, so we multiply and divide all that out, we get 286 kilojoules of energy, right? And that is energy that is absorbed from the environment, and so our reaction is going to feel colder when this reaction progresses. All right, so this wraps up our discussion of energy and chemical reactions. We'll do a little bit of practice with these in class and in Mastering Chemistry, and that will wrap up Chapter 9.